Today, we are diving into something pretty wild. It's about the collision of two of the most transformative technologies of our time. You've got artificial intelligence on one side and nuclear fusion on the other. This is a story about a truly monumental problem and an even more ambitious solution, one that could, fundamentally change our world.
Okay, so let's just start with this bombshell. This isn't science fiction, seriously. Reports are confirming that Helion, one of the leading fusion startups out there, is actually in talks to become the dedicated power plant for OpenAI. Yeah, the company behind ChatGPT. This one negotiation connects the dots perfectly, from AI's insatiable thirst for energy straight to the promise of harnessing the power of the stars, right here on Earth.
And when I say insatiable, I mean it. That demand is absolutely staggering. By 2040, global electricity needs are projected to surge by 60%. And a huge driver of that increase? Well, it's the data centers, the raw computational power that you need to train and run these ever larger AI models. It is a consumption crisis just waiting to happen.
So, that brings us right to the main event, the central question of this whole explainer. As AI's hunger for power becomes this critical bottleneck, a new high-stakes competition is really heating up. Who is going to win the race to build the clean, limitless energy source that's going to power our future? So let's meet the contenders. For decades, fusion was this thing that only massive government projects could tackle. But that's all changing. Now a new breed of private company is leading the charge, and they are moving at Silicon Valley speed.
First up, you've got Commonwealth Fusion Systems, or CFS. They spun out of MIT, and they're using a classic, proven reactor design called a tokamak. Think of it like a magnetic donut, a bottle for super hot plasma. But what's really interesting here are their backers. You've got industrial giants like Siemens and, get this, NVIDIA. So they're developing AI-powered digital twins to basically simulate their machine using AI to speed up the creation of the very power source it's going to need someday. Their goal? To be putting commercial electricity on the grid in the 2030s.
And then there's Helion. Their key backer is none other than OpenAI CEO Sam Altman, which kind of explains those high-level talks we mentioned at the start, right? Helion is taking a much more radical approach. They're trying to do something called a neutronic fusion. The goal here is to convert energy directly into electricity, completely skipping the whole steam turbine part of a power plant. And their timeline is incredibly aggressive. They already have a deal to supply power to Microsoft by 2028.
So, there you have it. Two major players with the same cosmic goal, but they're running this race with very different machines. To really get their strategies, we need to take a quick peek under the hood.
First, what exactly is nuclear fusion? Well, to put it simply, it's the process that powers the sun. You take two light atoms, you smash them together with just incredible force, and they merge into a single heavier atom. And in that process, a tiny bit of mass gets converted into a massive amount of energy. It's literally the engine of the universe.
Now here's the crucial part. You've got to understand how different this is from the nuclear power we have today, which is fission. Fission splits heavy atoms apart. Fusion joins light ones together. And as you can see, fusion produces way more energy, it's inherently safer, and its main fuel, deuterium, can be pulled right out of ordinary seawater. That makes it pretty much limitless.
And this just lays out the two competing race strategies perfectly. On one side, you have CFS with its donut-shaped tokamak, that magnetic bottle we talked about. On the other, you've got Helion's machine, which is linear, firing two plasmas at each other. But the biggest difference, really, is how they get the energy out. CFS uses heat to make steam, just like a traditional power plant. Helion, though, they're aiming to capture electricity directly from the magnetic fields. Their CEO compares it to regenerative braking in an electric car. It's a whole different ballgame.
Of course, a race this important needs a racetrack, right? And right now, governments all over the world are scrambling to build it. They're creating the regulatory rules that will let these amazing machines go from a lab experiment to something that actually powers the grid.
Over in the United States, the Nuclear Regulatory Commission made this absolutely pivotal decision. They decided not to regulate fusion machines like their complex nuclear reactors. Instead, they put them under a much more flexible framework. For the industry, this was a massive green light. It cleared away a huge mountain of potential red tape and basically put the path to commercialization on the fast track.
And this wasn't just some random decision. It's all part of a clear three-stage plan. They started with early preparedness, just getting the rules straight. Right now, we're kind of entering stage 2, where they start licensing the first prototypes. And the big goal is stage 3, a full framework for the mass production of commercial fusion machines.
And make no mistake, this race is global.
The UK, for example, became the first country to actually publish a national fusion strategy. They are explicitly creating a friendly regulatory environment because they want to attract investment and position themselves as a world leader in this brand new energy sector.
But let's be absolutely clear about something. This race is a marathon, not a sprint. Crossing that finish line means we have to overcome some of the most difficult scientific and engineering challenges humanity has ever faced.
So here's the core problem. To make fusion happen here on Earth, you need to heat fuel to temperatures that are hotter than the center of the sun. Yeah. Helion's target is 200 million degrees Celsius. Now, reaching that temperature is one thing, but sustaining it in a stable reaction that actually produces more energy than you put in, well, that is the grand prize of 21st century physics.
And okay, let's say you solve the science. You then immediately face what I'm calling the manufacturing mountain. Just look at this chart. It shows the sheer scale of the ramp-up. We're going from maybe a couple of prototypes today to needing 800 working reactors by 2030 and then nearly 8,000 by 2035. This is an industrial scale-up of a speed and complexity that is just unprecedented.
And look, don't just take my word for it. This quote from Helion's CEO really grounds us in reality. The key engineering challenge is going from a successful experiment, which is a single energy pulse every 10 minutes, to a reliable power plant that's running continuously, pulsing 10 times every single second. That leap is just monumental.
So the race is on. You've got these private companies, backed by the biggest names in tech, sprinting towards a goal that could solve humanity's energy needs and power the entire next technological revolution. The question really isn't if we'll get there anymore, but who gets there first and how our world will be reshaped when they do.